Well, hello, everyone. Thank you, Katie, and welcome to this webinar on observations and data collection, the first of 5 seminars in the NOAA Science Report Seminar Series. And the next seminar in this series will be held on February 23rd at 3 p.m. Eastern Time. I'm Tony Marshak, one of the NOS representatives on the NOAA Research and Development Enterprise Committee, a cross-line office committee of the NOAA Science Council. And this committee is responsible for the development of the NOAA Science Report with input from contributors across NOAA. The sponsors for this seminar series include the NOAA Research and Development Enterprise Committee, as well as the NOAA Central Library. And I want to thank the NOAA Library staff, especially Katie Rowley, for their valuable assistance. The NOAA Science Report is an annual report that highlights NOAA's scientific accomplishments for the year and reflects NOAA's research priorities. And the 2021 NOAA Science Report will be released shortly on the NOAA Science Council website, so please stay tuned. This science report spans the entire range of NOAA's mission, with more than 60 stories featured in the 2021 report. These are stories that represent the accomplishments of NOAA employees as well as NOAA's partners. Today, we're welcoming 4 speakers whose work features observations and data collection spanning NOAA's mission from satellites in space, hazardous weather events, to chemical spill impacts, and about animals at the bottom of the ocean. The full bios for the speakers today can be found in the website description of today's webinar, so I'll just give the names and affiliations of our speakers in order to save more time for their presentations. In order, our speakers are Dr. Paul Pennington, a research environmental scientist with NOAA's National Ocean Service from the National Centers for Coastal Ocean Science, Dr. Dvora Hart, an operations research analyst with NOAA Fisheries, based at the Northeast Fisheries Science Center, Dr. Michael Pavolonis, a physical scientist with the NOAA National Environmental Satellite Data and Information Service from its Center for Satellite Applications and Research, and Jeffrey Adkins, an economist with Integrated Systems Solutions Incorporated in support of NOAA's Performance, Risk, and Social Science Office. Each of the 4 speakers will give a 10-minute presentation, and then we'll have a question and answer session after all the presentations. So with that, I'd like to invite Dr. Paul Pennington to kick off our presentations. And Paul's presentation is entitled Field-Based Mesocosms, In Situ Deployments for Assessing Impacts of Chemical Spills in Coastal Areas. So Paul, if you're ready, I'll go ahead and turn it over to you.
Thank you, Tony. I appreciate the opportunity to talk about our science today, and I'd like to acknowledge my co-authors, Dr. Pete Key, James Dogamaw, Blaine West, and Dr. Marie DiLorenzo. I'd also like to identify our customers and collaborators. Our customer for this project is NOAA's Office of Response and Restoration, the Assessment and Restoration Division, and then we collaborated with the University of Texas A&M at Corpus Christi and had some student involvement on the project. The Office of Response and Restoration identified a research need for assessing toxicity after oil and chemical spills. And the need is essentially that transient or ephemeral data is often missed in terms of toxicity. So the objective of this project was to develop a field mesocosm platform to capture that transient or ephemeral toxicity data. So specifically the need was for an inshore or intertidal estuarine type system, a design that was ready to deploy with the appropriate species, and a design that was also applicable to several different geographic areas. After the Deepwater Horizon incident and the NERDA claim, mesocosms were used for that, but there were some issues that remained after that, and so ORNR wanted us to work with them to try to fine-tune and develop mesocosms in a more formalized way. So the overall goal is to improve preparedness in assessing near-term impacts during future spills. So what are mesocosms? What are field-based mesocosms? They're useful tools for assessing toxicity in oil and chemical spills. They're also called in situ deployments, in situ bioassays, or in situ enclosures. And in situ basically means that we're working in the natural environment as opposed to in the laboratory. In the most basic sense, a field mesocosm is a cage of organisms that are placed in the field, and the organisms are exposed to the actual conditions in the field, be they what they may. And they're indicators of harmful conditions, and as well as the length of time that the harmful condition is present in the environment. Specifically, for this project, we wanted to research various mesocosm designs and previous work that has been done, and then to choose the design that worked the best, choose appropriate species, and then perform real deployments in 2 geographic areas, and we chose South Carolina and Texas. And these are just reference sites. We did not actually deploy at real spill sites. This project was to more or less validate the use of the cages. And then we perform refinements during and after the deployments, and at the end we developed a standard operating procedure. We scoured the literature and looked at various types of designs, and this is a smattering of some of the designs that we found, not everything that we looked at by any means. We also spoke with a number of other researchers. We looked at commercially available products, as well as drawing on our own in-house experience. And the design that we chose was a cylindrical design. It's basically a commercially available bait pin that you can buy right on the internet, and it's a metal mesh coated with a plastic coating, a 1-inch mesh size, and then we basically covered over the bait pins with our own mesh size of smaller dimensions, 1/8 inch for fish and 1/16 inch for shrimp. And then we used 3 mesocosms for each species for replication. So we had 6 mesocosms total, 3 for fish, 3 for shrimp. And then the systems were deployed in South Carolina and in Texas at various times, and we assessed mortality at 7, 14, and 21 days. The site in South Carolina is at Leadenwaugh Creek, which we call our CTL site near Charleston, South Carolina. And this is a long-term reference site for many of our environmental studies that we do at the National Centers for Coastal Ocean Science. And in this particular deployment, we put 100 shrimp into each cage, each of the shrimp cages, and 25 fish into each of the fish cages. And we chose the shrimp Palomon pugio, which is a small grass shrimp, and the mud minnow, Fungulus heteroclitus. They're native to the area, and they were collected on site, deployed directly into the cages. The cages were deployed directly at low tide, and they were anchored to the sediment with metal rods. The site in Texas is in Rincon Bayou, which is near Corpus Christi in the Nueces Delta. And we followed the same exact protocol as in South Carolina. The only differences are that the species of fish that we used was Fungulus grandis, as it is more abundant there on the Gulf Coast than Fungulus heteroclitus. Also of note is that the tidal amplitude was much smaller in Texas. It's only about a foot or two, whereas in South Carolina, the tidal amplitude is about 2 meters or 6 feet. The results were very promising. We had excellent recovery of the organisms after 21 days. We were able to fine-tune the cages during the deployments to make sure that the animals were surviving. And then we observed various fouling situations and silting levels that occurred at the site to document that as well. The round cages performed really well. When we tried square or cubic shaped cages, the animals got impinged into the corners and died. In Texas, we had very similar results. We had excellent recovery of the organisms. Our collaborators at Texas A&M, working with a student, Elizabeth Harris, she was doing a student research experience. She was able to receive our cages. We shipped them out to her. She followed our standard operating procedure, deployed the cages, and had great results, which is our intention. We want this to be able to be a platform that someone can take the devices and the operating procedure and follow it and deploy it. It was a great collaboration. We do have some known issues. First is fouling in the summer and the fall, especially in South Carolina. The cages will get fouled very quickly. Silting can also occur, and this occurred in Texas and South Carolina. Basically, loose sediment, loose silt accumulates into the bottom of the cages, anywhere from 2 to 5 centimeters deep. We did lose one cage during a storm event. We found it 300 or 400 yards downstream at the South Carolina site. And then during the fine tuning of the cages, we had to come up with a different way of attaching the lid because we had some animals escape during the study, which was unfortunate. So in conclusion, they're not complicated and they're relatively easy to use, and we've deployed them in a very simplistic way, but there are a number of other types of deployment strategies that can be used, and they can easily be adapted to other species of the same size. Obviously, some species will not work due to their behavior or other ecological factors. We recommend not deploying the cages beyond 21 days, especially in high fouling areas. And we also recommend that you get the most bang for your effort by coupling your deployments with other sampling efforts, such as when you deploy hydrographic instruments, water quality sondes, or even passive or active chemical samplers that you may put in the environment. And finally, the exposed organisms can be used as biomarkers of exposure or effects. You can also retrieve the organisms from the cages and look at bioaccumulation or uptake, as well as possible follow-on laboratory studies for physiological experiments. So things to consider: how quickly can you get the cages out there? How many cages do you need? These are all things that need to be answered on site. And you'll need a reference site to compare to. Do you need permits to deploy these cages? Are the animals available? Some times of the year, organisms are not readily available. Can you get to the site? Do you need a boat? Can you drive to the site and walk in? And also there's the risk of loss. Anytime you deploy something out in the environment and you leave it unattended, you may return to find it not there. Sometimes storms take things away, and unfortunately, there's also theft that occurs. And anytime you work in a spill situation, there is a risk to human health, and you need to make sure your employees are properly protected when entering the water. And we have a number of products. Currently, we have 3 complete sets of the mesocosms stored in Charleston, and we have developed a standard operating procedure as well as a nice story map on the construction and deployment. And I would be delighted to share those with you all afterwards by email. And that brings me to the end, and I appreciate your time, and thank you very much.
All right, excellent. Thank you so much, Paul. That was a fantastic presentation. I'll go ahead and introduce our next speaker, Dr. Dvora Hart, and turn it over to Dvora once she's ready.
All right. So this is about detection of underwater animals using a towed camera system and automated image analysis. You see an example of that on the first slide here. Now, next slide. The sea scallop fishery is one of the most valuable fisheries in the United States, worth over $500 million at the dock. It's a remarkable management story of recovering from pretty severe overfishing to being really an example of innovative management and science. The traditional way that the fishery the scallops were surveyed was using a dredge, modified fishing gear, basically. And it gets towed on the bottom for 15 minutes, gets hauled up, the catch gets dumped on that table you see there in the upper left, and then people have to sort the catch and then measure scallops and fish. It's a quite time-consuming procedure. We end up doing less than 1 dredge tow an hour. So about 10 years ago, we developed a more modern method for surveying scallops and other things that are on the bottom, known as HabCam. This is a partnership between NOAA and the Woods Hole Oceanographic Institution, and there was also commercial fishermen involved. So you see in the lower right picture of the vehicle. So there's a metal frame there, and on the it has 2 cameras, stereo cameras for 3D observations, and 4 strobes, lights around the camera. Up on top, there's a side scan sonar, downward looking, and a large array of oceanographic sensors. On the upper left, you can see it on the research vessel. We still do some dredge tows, both to continue the time series and to collect physical samples. And so you see the dredge in the middle, and on the left, you see the HabCam vehicle, and you can see the fiber optic cable that connects to the vehicle. The HabCam takes about 6 images a second, or about over 20,000 images an hour. And so it's a huge change from the dredge, which was collecting basically 1 observation an hour or less. Just to show a few pictures of what we can get from HabCam, this is a scallop bed on George's Bank, some adult scallops, and then you see some juveniles as well. These are swimming scallops. Our scallop is one of the best swimming scallops, and you see 3 of them there. There's more than 1 shadow per scallop because there's 4 lights, and so in this case we're seeing 2 shadows per scallop. The images actually overlap, so we can splice them together. If anyone's taken a panoramic photo, it's the same sort of idea. This is a mosaic of 4 photos showing a high-density scallop bed off of southern New Jersey. We also see fish, and just to show a few examples from the upper left, that's a little juvenile summer flounder, and going clockwise, a barn door skate, a goosefish or a monkfish, and a Atlantic cod. There's lots of talk about ecosystem-based fishery management, and my opinion is that it's in order really to do this sort of thing, you need observations that are ecosystem, that you can actually see what's going on. And this shows a couple examples. On the lower left, you see a mob of Asterias vulgaris sea stars that are attacking a scallop. And on the upper right, you see a crab next to a recently dead scallop that presumably it killed, and you can see it actually has a piece of the scallop in its pincher. When I go back, my all-time favorite HabCam picture, this is actually a mosaic of about 4 photos put together. These are monkfish, and monkfish generally, they're cannibalistic, so they generally stay away from each other. So this is almost surely a mating interaction. The females are larger, so you see the big one on the upper right is a female, and it looks like she has 5 male suitors. But you notice they're not stupid. They're approaching her from behind, so they do not want to get near her mouth. So doing HabCam was a big advance, but once there's a solution, there's always more problems. So one of the problems is that we collect about 5 million images a year on the survey, and we manage, and it's a very difficult task to even annotate 2% of them, that is to mark the images. Here's an example. So that's very labor intensive, even to do 2%, which is 100,000 images. So I was fortunate to participate in a NOAA strategic initiative involving all the science centers where we developed some automated image analysis, and through our partners in Kitware as well. What I'm going to show you uses convolutional neural networks, which is a real breakthrough in artificial intelligence. They kind of work like a human brain, and so you train it using large amounts of manually annotated data, and then it works out picks out what scallops and so on are. This is an example here. All the yellow boxes were drawn by the computer. They get confidence levels. So there's scallops. It also picked out a crab there. You might notice it missed a couple of them, which is still a bit of an issue, but it's certainly tremendous progress. Besides scallops, we've developed detectors for fish. So and crabs. So you see detections of fish, crabs, skates. It's been used, this Viami tool has been used for lots of other purposes. One I can mention is it's being used to count seals and sea lions from aerial photos. One important task is to compare the automated with the manual annotations. So here's a couple examples of that. The yellow boxes are the the automated annotations. The blue or cyan lines and boxes are what a human did. On the upper left, you see basically perfect. The automated annotator found all the scallops and the fish, as well as the manual annotators, and so they're in a perfect agreement. We have harder time with really challenging images, which is on the lower right. Most of the scallops were found, but there's a few of them. You can see in the purple lines, you can see in the lower left and then kind of in the middle. There's a bunch that the manual annotator found, but the automated annotator did not. In defense, the manual annotator, it's difficult to annotate an image like this, and the manual annotator missed a few scallops that the automated one caught. So it's best to try to combine these things so that we get the best information possible. So just some ongoing work. We're still always trying to improve the automated annotations. They're doing very well, but there's always a room for improvement. As I mentioned already, we're doing work to combine the manual and automated annotations to get something that's combined that's better than both of them. We have one paper out on this, but we're working on more. It's also possible to use the automated annotators to QA, QC the manual annotations. That is, we can, if the automated annotator finds a scallop that the manual one did not find, those can be listed and then they could be double checked to see. I'm going to have a summer Howling student whose job is going to be a computer science major. And her job is going to be develop detectors for things that we haven't worked on yet. Things like sea stars, sand dollars, anemones. There's all sorts of things in these images. And again, I think people are interested in benthic ecosystems. This is really what we need to do. Finally, to end that if you want to work with this VIAMI, it is open source and available to the public. It's being used all over the world now. And there's its URL down on the bottom. Okay, that's it.
Thank you so much, Dvora, for that great presentation. I really appreciated the many nice images and certainly your point about the importance of observations for carrying out ecosystem-based fisheries management. Our next speaker is Dr. Michael Pavolonis, who will be presenting about an artificial intelligence tool that improves severe weather warnings. So please take it away, Mike.
Okay, thank you, Tony, and good morning, good afternoon. I'm from the NOAA National Satellite and Information Service, Center for Satellite Applications and Research. I'd first like to acknowledge my project partners at the University of Wisconsin Cooperative Institute for Meteorological Satellite Studies. In particular, John Centennial, he did much of the work on this project. I'd also like to acknowledge our collaborators at the National Weather Service and the NOAA Office for Oceanic and Atmospheric Research, who are vital to the success of the project. So today I'm going to talk a little bit about a new artificial intelligence tool that is helping the National Weather Service forecasters identify severe weather threats in developing thunderstorms. So first off, severe weather is not that uncommon in the United States. In this past year, there were over 18,000 reports of severe weather, where I'm defining severe weather as damaging straight line winds, hail that has a diameter of 1 inch or greater, or a tornado. And it's really not uncommon to get more than 20,000 severe reports in a given year. As you can see in the map on the left part of the screen, these are the severe weather reports from 2021. So severe weather occurs in every state. It's obviously more common east of the Rockies, but it does occur in every state. And although it's more common in the warmer seasons, severe weather is possible any time of the year. We know, of course, last December was very active for severe weather. So, in response to the severe weather threat, the National Weather Service issues severe thunderstorm and tornado warnings when severe weather is likely imminent. These warnings are important. They alert people in harm's way to take protective actions. Now, the quality of the environmental data used to identify severe weather threats is increasing. For instance, NOAA's weather satellites can now sense lightning and capture images of developing storms every 30 seconds. The quantity of environmental data is also significantly increasing. For example, weather satellites alone provide over 1 trillion observations every single day. That is about 7 times as many compared to just 7 years ago. This is where artificial intelligence comes in, as it's a critical tool for transforming large volumes of data into actionable information. And our research team developed an AI tool that helps the National Weather Service identify severe weather threats with greater confidence and, in many cases, lead time. So the name of the artificial intelligence tool that we developed is ProbSevere. That's short for probability of severe. ProbSevere transforms data from multiple sources, including computer forecast models, satellite, radar, and lightning detection sensors, into the probability that a developing thunderstorm will produce either severe wind, hail, or a tornado, or some combination. It's designed to provide lead time. Typically, it provides lead time in the range of 10 to 40 minutes ahead of the actual occurrence of severe weather. So this is a tool that's designed to identify severe weather threats before severe weather strikes. The model is made possible by machine learning, which is a branch of artificial intelligence. So let's look at a couple examples that illustrate how the ProbSevere tool works. So we created a radar-based interface where the probability of severe weather from ProbSevere is conveyed to a user using a color-coded contour around the perimeter of each distinct storm cell that you can see in radar. So I'm going to bring up an image here. And in this radar image from a couple of years ago, you see the radar echo of a thunderstorm in the center of the image. You know, just like the echoes you would see on your favorite radar app when there's active weather. The magenta contour around the perimeter of the storm corresponds to a severe probability of more than 90%. The yellow polygon is the National Weather Service severe thunderstorm warning, and this storm did go on to produce severe weather. Now, as you'll see in the next example, the severe probability, again depicted by the color-coded contour around the coherent radar echoes, generally increases ahead of severe thunderstorm or tornado warnings. And so you'll see in this animation, which we'll play a couple times because it goes kind of fast. In this example radar animation, you'll see a cluster of thunderstorms moving across northern Illinois. Note how many of the storms have severe contours that quickly turn magenta in color, which means the probability of severe is significant, at least 75%. You can also see that severe indicates a high probability of severe just in advance of the severe weather warnings appearing on the image. Those are the yellow and red polygons. So the way this works in operations, National Weather Service forecasters use severe to identify severe weather threats earlier with added confidence. So if severe indicates a high likelihood of severe weather, and traditional forecaster analysis of radar and other data sources finds trends consistent with the development of severe weather, then the confidence is high that the storm will evolve into a severe weather maker. So this really, I think, illustrates the value of combining human and artificial intelligence. Okay, so severe was just deployed in National Weather Service operations only after extensive testing in simulated operational environments, such as the NOAA Hazardous Weather Testbed. The decision to transition severe to operations was largely based on feedback from forecasters participating in the Hazardous Weather Testbed. And in that testbed, the majority of forecasters indicated that severe consistently added confidence and lead time to severe weather warnings. So the NOAA SIMS, for the Cooperative Institute for Meteorological Satellite Studies, severe artificial intelligence tool, helps weather forecasters identify severe weather threats with greater confidence and lead time. This is a tool that was successfully transitioned from research to operations this past year. I think the project is a great example of multiple NOAA line offices and academic partners working together on research and that transition of research to operations. It's, I think in a more general sense, artificial intelligence and those techniques are really critical for transforming enormous volumes of environmental data to information for decision making, because the data volumes are just simply too large to rely only on human interrogation of those data. It's not a replacement for the human, but it's a force multiplier. So with this project, we have successfully transitioned to operations, but there's more to come. So we've now expanded the project to include artificial intelligence for lightning prediction. And this is just a preview of that. So the experimental lightning prediction tool is known as LightningCast. LightningCast is an artificial intelligence capability that can predict where lightning is most likely to occur up to 60 minutes in the future. Again, it's trying to predict where lightning will occur before it occurs so people can take action. It could even predict which clouds will produce lightning prior to the formation of rain. So if you're looking at your favorite radar app and you don't see any rain or echoes on there indicative of rain, this model still may be able to pick up on developing clouds that will eventually become a thunderstorm and produce lightning in that location. So that can give people more time to seek shelter before lightning strikes. You could think of this as being especially important in sort of large outdoor gatherings, festivals, stadiums, things of that nature. So over the next 12 months, LightningCast will undergo extensive testing, and if that testing is successful, it may become another artificial intelligence-based operational tool for forecasters. And if you're interested in learning more about either Prob Severe or Lightning Cast, I have a couple of QR codes there that will take you to websites that are a good launching off point for more information. And with that, thank you for your time.
Right, thank you, Michael, for that really nice talk. It's very interesting work and great illustration of AI applications, as well as those cross-line office collaborations that you mentioned. And so our final speaker then is Jeffrey Adkins. Jeff will be presenting on a GeoXO economic assessment. So Jeff, please go ahead when you're ready.
Yeah, so over about the past year, I've been working with a team of folks on NOAA's future generation of geostationary satellites called the GeoXO. I've been studying the benefits and costs of that new constellation. The geostationary satellites, they fly at very high altitudes, which allows them, their orbits to be synchronized with the rotation of the Earth, which means they look down on the same field of view all the time, and they can provide nearly continuous observations. The current series of geostationary satellites will reach the end of their operational lives in the early 2030s, and at that point they'll be replaced by satellites from the GeoXO series that are in planning right now. The current plans for the GeoXO satellite constellation includes 5 instruments. They have an imager, an infrared sounder, a lightning mapper, an atmospheric composition instrument, and an ocean color instrument. Right now, the GOES-R series has an imager and a lightning mapper, so the plans call for the addition of 3 new instruments. And as part of this planning process, I'm working on a benefit cost analysis, and we'll be presenting the findings to NOAA and NASA and Department of Commerce later this year. As a general rule, we say the value of information is 0 until it is used to improve a societal outcome. GeoXO observations will be used to create new information resources or improve existing information resources, things like forecasts of weather and harmful algal blooms and air quality. GeoXO creates value for society when these new and improved products are used to reduce people's costs, increase productivity, and improve human health and safety. So this raises a number of questions. What information resources will be improved by the GeoXO observations? That's a long list. Who uses the information resources that will be improved? That's an even longer list because a single product often has many users. And most importantly, what's getting better as a result of using these information resources? Answering this question means we need to know about the decisions that people are making that are going to be informed through the use of products improved by GeoXO and the way that the outcomes will be improved. One example of this is the aviation industry. They use short-term weather forecasts to make decisions about when to ground aircraft because of bad weather and when to allow normal operations. The cost of error associated with this particular decision is about $2 billion a year. One of the goals of NOAA Pathfinders is to work directly with users like the airline industry to find answers to the questions I listed above. The Pathfinder effort is guided by something called the jobs to be done theory. The basic idea behind that was summarized by a professor at Harvard Business School, Theodore Levitt. He said people don't want to buy quarter-inch drill bits. They want quarter-inch holes. So when you apply this thinking to GeoXO, we look at the jobs that need to be done. The theory says that people use NOAA products and services to get jobs done, things like preparing for a hurricane or deciding how much electricity to produce tomorrow, deciding when to issue air quality warnings, things like that. Or something as simple as deciding whether to take an umbrella to work. We need to know about how people use the products that will be improved by GeoXO to estimate the benefits of GeoXO. We organize the answers to these questions in a framework called value chains that show the linkages between the observation, the product that's being improved, the user use, and ultimately the outcome that's going to be improved. This provides a framework that helps us make sure that the estimates of benefits that we come up with reflect an accurate understanding of that complete pathway from improved observations to increases in societal value. The idea behind this analysis, it's a very simple idea applied to a very complex system of everyday users. The idea itself is simple. For each use case, we compare the outcomes that are expected to occur with and without GeoXO observations. And the difference between those is the benefit of GeoXO. An example of how this works is with the electric power industry. The electric power companies decide how much electricity they're going to produce based on energy demand forecasts that are greatly affected by forecasts of weather, of moisture and temperature, and other attributes of weather. Energy error in the energy demand forecast is very costly. In some cases, load forecasting error leads to producing too much electricity. So utilities incur the cost of producing electricity that will not be sold. In other cases, load forecasting error leads to the production of too little electricity. In those cases, utilities must purchase additional electricity at a much higher cost than the spot market. GeoXO observations will improve forecasts of weather variables that drive energy demand forecasts, and this will reduce load forecasting error and reduce the cost of producing electricity. So in this example, the value of GeoXO is estimated by comparing the cost of load forecast error in two cases, one using GeoXO observations and one without those observations. So it's a simple idea, but the system that it's applied to is very complex. The figure shown here is actually a simplified version of what we found so far. The 5 GeoXO instruments are shown on the left, and in the middle column are very broad classes of NOAA products that will be enhanced by GeoXO observations. Each instrument contributes to NOAA products in different ways. The analysis is further complicated by the fact that observations from one instrument often make those from other instruments more useful. The complementary nature of GeoXO observations is by design. These instruments were chosen to work together. On the right-hand side are broad classes of societal outcomes that these improved products are expected to affect. A single product may be used by different users to improve societal outcomes in different ways. Each of these pathways you trace through with the arrows going from left to right is a separate value chain. It's a separate way that GeoXO is expected to produce value. And our studies so far have identified more than 150 value chains. much of the information that we have on users and decision-making and improved societal outcomes comes from an extensive ongoing user engagement activity called NOAA Pathfinders. GeoXO is the first time we've used the Pathfinder approach. It's kind of a front line of sophisticated end users that constitute a community of early adopters for satellite information. They play a key role in connecting instrument data to an area of societal value. Information on these linkages is framed using value of information and jobs to be done theory. As I mentioned before, the GeoXO Pathfinders are participating in these current value studies. They're helping us to develop the value chains that communicate the connection of GeoXO science to societal decisions and operations. NOAA Pathfinder, they do include plans to conduct value studies after the launch of GeoXO that focus on the actual use of data and products. So kind of a recap, the GeoXO team has identified more than 150 different ways that GeoXO is expected to generate societal benefits. So far, benefits have been estimated, quantified for 7 of the 150 value chains. Several factors affected our decision on which value chains to quantify. Obviously, we try to focus on use cases where we expect the values to be large. We also select use cases that will show the value of each of the GeoXO instruments that's considered in current plans. And we are limited by the existence of data in some cases and our understanding of complex value chains in other cases. Over the next several weeks, we'll be quantifying other value chains, and as each one is complete, we vet the results with the GeoXO instrument teams and the user teams. And at the end of the summer, we'll be presenting these results to the Department of Commerce, NASA, and NOAA officials who are leading a system requirements review for GeoXO. And that's all I have.
All right, well, thank you, Jeff. That was an excellent presentation on examining the value of GeoXO. And I just want to say thank you to all our presenters for your great work and super informative talks. I'll now like to open it up for questions from our audience, and I'll go ahead and turn it back over to Katie to start off our Q&A portion.
Great, thank you so much, Tony, and thank you all to our presenters. Attendees, as I've put in the chat, you can place your questions in the question panel. But to kick it off, we do have a few questions. The first one is for Michael. What did you find particularly helpful for ensuring the successful transition of the ProbeSphere tool into operations?
Yeah, thank you for the question. So, this cross-line office collaboration was really critical. So, we're partnering with the National Weather Service on that transition. They are the users, they are the primary stakeholders. So we were closely partnered with the National Weather Service. We also partnered very closely with the Office of Oceanic and Atmospheric Research because we were relying on some of their data sets, some of their radar data sets. Without that collaboration, I think we would have had a hard time achieving the result that we did. So collaborating early and making sure that those collaborations remain strong was critical.
Great, thank you. I have another question for Jeff. How do you handle the compilation of value chains for components that have unknown value estimates or range of estimates?
Could you repeat the question? I want to make sure I understand it before I give an answer.
Of course. How do you handle the compilation of value chains for components that have unknown value estimates or ranges of estimates?
Yeah, so I mean, that's a common problem. If I understand the question correctly, obviously we're dealing with imperfect information, and so a number of key variables play into the final answers that we come up with. A couple of critical variables is what is the impact of the phenomena that is being measured, whether it's convective storms or tornadoes or hurricanes or harmful algal blooms. What is the impact? And a second related question is what portion of that impact is avoidable through some sort of mitigating action? And then that really is your potential universe of benefits. And then the third question, which is also critical, is to what extent can the observations from GeoXO help you avoid that avoidable component of the cost associated with that hazard? And those are key variables. In some cases, we have been fortunate enough to find answers in the literature. In other cases, we are looking to internal NOAA data sets on the contribution that these observations make to certain types of decisions, and in other cases, relying on expert judgment. And we present the findings as a range of values, and that's meant to kind of capture the most likely range within which each benefit might fall.
Great, thanks, Jeff. Our next question is for Deborah. Have you been able to apply the information captured in HabCam to conduct habitat assessments for other common species in the area beyond scallops?
Well, there's been some work on that, but we need to do a lot more to make that information available, and part of it, this artificial intelligence, so that, because usually I haven't been marking all these habitat information, other benthic organisms and all this type of stuff, and the artificial intelligence is going to be a way of getting all that information out there. But it has been used, in particular, there's a New England Fishery Management Council habitat PDT, or technical committee, which has used a lot of HabCam data to help design habitat protected areas and so on. But we have a lot more to do with that, for that.
Great, thanks, Deborah. This is a question for Paul. Are there other marsh species in addition to killifish and grass shrimp that you've been able to examine in your studies?
Using the current cages, we have not, but historically, we have deployed a number of animals in cages for unrelated studies. Many years ago, we've deployed mysid shrimp. We've deployed sheepshead minnows, which are a very similar shape and size to the killifish. Other researchers have deployed larger shrimp, such as pink shrimp or white shrimp. Unfortunately, those are basically the type of shrimp that we eat, basically, but they tend to cannibalize one another when they're crowded into cages quite readily, unfortunately. There's also been some work done by some of our colleagues at the South Carolina Department of Natural Resources, deploying shellfish such as seed clams and oysters in the field. And so there's quite an array of species that could be used, but there are some limitations, of course.
Great, thank you, Paul. I believe that is the end of our questions. And with that, I hope everyone has a safe and enjoyable and a healthy rest of their Wednesday. Thank you all, and thank you again to our presenters.